So we saw we can halogenate alkenes, dienes, and alkenes at the allylic position. So we can kind of brominate there using radical reactions, and we saw that if the alkene's not symmetrical, you can get two different products. You can get something called the kinetic product and something called the thermodynamic product. So that will be a kind of a highlight in this semester. You can get two different products based on a change in temperature. So chemistry allows you to do that. You can actually control the outcome. So it's kind of not randomized anymore, okay? All right, so kinetic product comes from, well, we'll talk about how this forms. So let's talk about the mechanism. Okay. Did we get over? I don't think so. All right, so let's talk about the mechanism here. By mechanism, I'm talking about how do these two products actually form, okay? So we have our double bond here. All right. So if we look at where the bromine is coming off, the radical probably is forming off this hydrogen. All right, so the bromine radical is going to take a hydrogen. Like so. So this is a radical mechanism. So you should have in total 3 arrows in each step. Okay. So this will give us HBr. And then we have the radical on this position. Okay. All right. Well, we have a radical next to the double bond. So what else can we draw in addition to this structure? What do you guys think? Also, what else can we draw? We could probably draw a resin structure, right? So where would this radical also show up? On what carbon? Yeah, to the left, right? So let's show those arrows just to see how that works. So we're going to draw 3 arrows again, draw a different resin structure. So now the double bond is going to slide over one position, and then we generate a different radical here, okay? So remember the resin structures, right? They paint one picture of the whole molecule. So the electron distribution here, the radical is going to be, at these 2 positions, some percentage of the time, right? So which one here is the more stable radical? So which resonance form is more significant for the radical? If we think of radical stability. Which one?
The original structure.
Yeah, the first structure we drawn, right? So that's a secondary radical. That's more stable than a primary. So we have actually a more stable radical here. So more stable radical. So that's going to be more significant. So the radical is going to stay at this position in the overall picture. It's going to be a higher percentage at this position. So this is actually going to react the fastest with Br2. Okay. Or, the Br2 here, okay, so Br2 we're going to add. So how exactly this forms is exactly how we did it above in this mechanism. So you're going to have the radical here, and that's going to attack the bromine molecule to regenerate the bromine radical here. So I'm not going to draw the arrows because the arrows here is already trying to show you the direction to the resin structure. So I'm just going to draw this here and just draw the product. Okay, so more stable radical. So in this case, we get the kinetic product. So this forms the fastest. So this product is called the kinetic product. So here, forms faster. So that is our kinetic product. So we got two possibilities here. Okay, so that product, and then, bless you, we use this radical here. Again, reacting with Br2. So what this radical is doing, it's going to regenerate here, and then what comes out of here is Br radical. So you're substituting bromine for this reaction. So bromine radical is going to come out of the reaction and regenerate that radical, go back to this original step here. Now here we get the bromine at this position. So we've added this bromine to the terminal carbon atom, okay? So here we have the more stable product, more stable. Here is more stable because the more substituted alkene is formed. More substituted alkene is formed. Okay? And so this is the thermodynamic product. More stable alkene. Okay? So it's thermodynamic because to get to this reaction, you have to elevate the temperature. When you elevate the temperature, chemistry is often controlled by thermodynamics. So if something can equilibrate, you're going to keep going back and forth until the most stable product is eventually formed. And then the reaction typically ends after that. So you have to leave it running for some time to get the thermodynamic product. Okay? Most times in chemistry, we don't let that happen. Our reactions are short, low temp, and the kinetic product is formed predominantly. Okay? All right. Are any questions how we differentiated those two mechanisms? It's the radical intermediate that plays an important part in how it turns out. Are any questions about that? Okay. So if this doesn't make a lot of sense, let me go over a graph here that kind of tells us how this plays out on a chemical level, okay? So I'm going to draw a graph. So let me scoot this up a bit. So let's draw a graph here. Here's my y-axis. Here's my energy. Now I'm going to map that same reaction here, okay? So right here in the middle, I'm going to write my reactants. So I'm going to do, and here's NBS. So remember, that's the reagent we use to generate the bromine, to generate the bromine radical. Okay. So we're going to say, eventually, this goes to a point where this radical is formed, okay? But eventually, it goes to the lowest energy here, and that's my product. So that's my more favorable product. Br going to the internal alkene, the more substituted alkene right here. All right, so right here we have the more stable product. So this is just not limited to radicals. We'll see this too when we generate carbocations again, okay? So the more stable product here. All right. Then on this other side, so this reaction can go through two different types of intermediates, right? It can go to this radical, or it can generate this radical right here. So let's draw a line under here, okay? Okay, but you see here that these radicals, they can equilibrate. So you can actually go to a product and go back to the radical, and then you could go back to the other radical. And then you see here that depending on the type of conditions you have, you can either go to the right, to the far right product here, or you can actually fall down and go a slightly higher in energy right here. So this will be higher in energy, but the kinetically favored process, the less substituted alkene. All right, so less stable. Less substitute alkene. All right. All right. So this one forms faster. So this is the kinetically controlled product. Forms faster. Okay. This is the more stable product, but it's formed more slowly. All right, and it forms slowly because you have to go through the least stable radical, the least stable, least substituted radical right there, and that's what causes the reaction to be either controlled by temperature / time. So here's reaction progress. All right, so we got to keep that in mind that there's a few ways this reaction can go based on its where the radical ends up. Okay. All right. Are any questions on how we saw kinetic product versus thermodynamic right there? Any questions about that? Anything we need to clarify? Are we okay? Okay. So radical reactions, that's one part, that's one type of reaction that these delocalized pi systems can undergo, okay? So let me just put that there. Now let's talk about some different reactions. Hydrolysis. Isomeric. So when we have allylic chlorides, we can get different products, okay? Kinetic and thermodynamic control. So let's talk about kinetic and thermodynamic control. Okay. All right. So if you start with these allylic chlorides and you add water to them, water can either add in this fashion or in this fashion, depending on what position it attacks, okay? So let's go over the mechanism. How does this work? So this mechanism, being able to write this mechanism, I think is important. So let's see here. All right, today is the 27th, so yeah. I forgot. All right. So, how does each of these products form? All right, so the mechanism here. So the generic mechanism, instead of a radical, what are we going to generate first? What kind of reactive intermediate? No, not a ketone. Wait, ketone? Maybe I heard that wrong. What's going to happen first? Any ideas? So we're going to generate this chloride ion. So this chloride is actually going to leave right here. Okay. So what happens here, we're going to generate a carbocation. And what can the carbocation do? Resonance, right? So we can move the carbocation to this position, right? Move this bond over right here. You get that carbocation, okay? All right. And then once this carbocation moves, okay, it will give us products here, okay? Oops, my bad. Let's go back. Oh, my bad. Oh, sorry. I meant to, sorry, don't write this. I meant to just write that other product. Sorry. Let's erase that. Okay, so that's how these chlorides can interconvert, right? The chlorine could actually come back and attack this position. So the chloride here could actually attack right here. All right, so that's how we get the isomeric chlorides. You can actually go through so in solution, if it's in solution and this chloride could leave, you can actually generate the carbocation intermediate, and that's how it kind of isomerizes. So that's kind of one of our limitations with these reagents. They're pretty sensitive, okay? But let's talk about how we form the kinetic product and the thermodynamic, all right? So formation of the kinetic product. All right. So we have the carbocation. Water can float around and attack at this position. Okay. Now we get the intermediate alcohol, protonate alcohol. So here, this is the more stable intermediate. Okay. All right. So if you have water present and you have an extra hydrogen to this oxygen, a most reasonable step to get rid of this excess hydrogen atom or proton is just to use another water molecule and remove it like so. Okay, like that. And then if we do that, eventually equilibrium will will favor the formation of the alcohol, and you get the first product here, which is the kinetic product, the allylic alcohol, the secondary allylic alcohol there. Okay, so that's the kinetic product. But how does the thermodynamic product form? Well, instead of attacking there, we would favor the formation of the alcohol at a different position. So which carbocation would we use here for the thermodynamic? So not the same carbocation we just used, right? Which one, the secondary or primary? Yeah, the primary, the one that has the more stable alkene already present in the molecule or intermediate. This one, yeah. So this is the only situation we can have primary carbocations. It's resonance stabilized. Okay, just reiterating that. All right, so same steps, just different intermediate. So make sure we could draw these steps here, okay? Boom. And then water forms right here. And then you're not done with the mechanism, so I recommend drawing out these electrons here. Okay? All right. So what happens here is you will get another water molecule. Okay, and then we get this alcohol right here. Okay, so you get the other product that can form, and then you're going to regenerate the acid. So you're going to, one of the water molecules will just be protonated here, and the acid will form. And then you would work this up by probably just treating this acid, but that's not important. Okay. So that's how we have two different products, forming from the same starting molecule. Okay, so you can go through these different structures here. All right, are any questions on this one? And the only difference from the other reaction is you're generating a carbocation instead of a radical. So you can also do different kinds of reactions here. All right, but any questions on that example? Catherine?
Why does the kinetically controlled product like the less stable one?
Like you mean like it's the less stable product?
Yeah.
So it has to do with the intermediate. So I would think about the intermediate that forms. So if you have a more stable intermediate, it tends to just react faster, even though if the energy of the product is not as stable according to thermodynamics. Okay. So that's when the reaction's kind of starved of energy. If there's like not enough energy, it's not going to climb up the activation barrier enough, so it won't be able to overcome the formation of the more stable product. So it's just because a product is more stable, that doesn't mean it's kinetically like fast, or it's not the fastest. It doesn't have a low activation barrier. So it just depends on the level of the reactants energy and the products. So we can even if something seems fast in terms of a reaction kinetics, it doesn't mean it's the most stable. So it can still go backwards if you give it enough energy to kind of push it that way. Yeah. So I would just say, look at the intermediates. So in this kinetic product, you're going through the secondary carbocation. And then this one here, the thermodynamic, it's still stable. It has resonance, but it's primary, right? Secondary carbocations are more favorable, so they form the fastest because they're the most stable. I know that what probably just said kind of counteracts that, but that's just an intermediate, right? It's part of going to the reaction. So I would say look at the intermediate to determine like why it happens faster, and then don't think of intermediates as the most stable state or stable part of the reaction. It has to go to a product, so that's why we evaluate the product stability by looking at where the double bond is, because that's where alkenes are stable based on the number of substituents attached to it. Okay. Any other questions on that? So I know this kinetic thermodynamic thing might sound a little bit weird. We'll actually see this in lab, like a reaction. If you leave it to go for like a week or something, it'll form the thermodynamic product and not the kinetic product. So it's based on kind of the mechanism here, the intermediates that are used to form it. Okay, any other questions? All right, Brianna's here. Good. All right, so let's go over a few more. So this was an example of what kind of mechanism, SN1 or SN2? Oh, thanks. So let's look at these steps. Is this an SN1 mechanism or SN2 mechanism? Do you recall what SN1, SN2 is? So SN1 requires the leaving group to leave first, right? So this is an SN1 process. So see here, we can actually get the primary carbocation to form if we have a double bond nearby. Okay, so that stabilizes the carbocation. All right, now let's talk about the other most common mechanism there. Allylic halides. Can undergo SN2 reactions. All right, so we'll talk about a little bit why this happens, okay? So if you have an allylic chloride here, and you have a good nucleophile, good leaving group, so chloride, remember, conjugate base of a strong acid, great leaving group, very stable conjugate base. So here, if we just heat this up, just lightly here, 50 degrees, and put a pour a product solvent, acetone, you can get the substitution to happen very cleanly. I would hope there. And then the chloride will be right here. Okay, so most of these, when you have a good leaving group and a good nucleophile, the rate of reaction is often, there's competing reactions. Typically go back and forth, but there's ways you can actually push it forward here. So you push it forward here. So the relative rate of this one is 73, and then if we take the similar reaction we've seen previously, no double bond, just a traditional SN2 mechanism, same nucleophile, same temperature, and same solvent, you get the fully saturated iodoalkane and the same conjugate base, Cl minus, or sorry, the same base, leaving group that comes off. But this rate is the slower of the two. So the double bond is clearly doing something, okay? So in terms of reaction rates, you look at the mechanism and you look at the transition state, okay? So I'll just mention a few points here. So presence of double bond. So it doesn't. So it actually doesn't matter which double bond it is. It could be a CO double bond or a CC double bond. They will both influence this rate. Okay. So presence of double bond makes reaction faster. Okay. All right. So let me just bring up a few points why this is. One, the sp2 carbon is an electron withdrawing group. Remember how we said atoms with more S character orbitals, they are stronger acids. So they're more electron withdrawing because the nucleus is closer to the electrons in the carbon atom. So it pulls the electrons greater. So it makes them, it makes the reaction more polarized, okay? Making opposites attract, okay? So we can say here that the allylic carbon is more electrophilic. Is more electrophilic. Okay? All right. And the second reason is, number two, the double bond. So I think this is more important. The double bond overlaps with the p orbital that is forming in the SN2 transition state. Okay, so overlaps the p orbital in the transition state. Okay, so this is the transition state, and when it does this, it stabilizes the transition state. So if you stabilize the transition state, you lower the activation barrier, okay? So it lowers the activation barrier. Lowers activation barrier. All right? So the barrier, if we kind of think of this graph, the barrier will now become lower here. So the barrier lowers. All right, so the barrier of the reaction is affected if you can stabilize any part of the reaction near the transition state. Okay, what does this look like? So let me just draw that example here. We have a double bond. Okay, let me change this pen. The double bond has p orbitals. And here is my bond. So I'm going to have a bond here. When a nucleophile approaches this the carbon atom right here. So here's the carbon atom. Here's the carbon. When the nucleophile approaches that, okay, it's going to start breaking that carbon halogen bond, the carbon chlorine bond. And that sp3 hybridized orbital is going to start to revert back to a p orbital, okay? And the s character is going to start to disappear and become more spherical there, okay? So we go back to an s orbital here, and then what happens here is that when the orbitals start to rearrange, they'll form a new sp3 orbital with the iodine. So it goes back to this p orbital, empty one here, okay? And then if we draw the other chlorine, the chlorine is starting to leave, so it's going to use its p orbital and depart. So this orbital here is now starting to depart. Partially negative still over here, partially negative over here. And if we put this whole thing in brackets, that could be our transition state. And you see here, there's some overlap between the p orbitals here. So this p orbital could actually interact with this p orbital and stabilize this, this bond breaking. So if it stabilizes that bond breaking, it just influences the rate, increases the rate dramatically. And that's why it this rate is so much faster compared to just the regular SN2 reaction we know. Okay, so that's my explanation. Sometimes instructors, they just tell you that it goes faster, but this is the reason why. Okay, so there's a little advanced explanation here using orbitals, but that's pretty much the way to explain it. Okay, but are there any questions on how this picture helps kind of explain the stability there? So it's all about orbitals, and chemistry is all about orbitals.
Can you zoom into it something?
Huh?
Can you zoom into like
Yeah, sure, right here. So you see here, interaction between p orbitals and p orbitals. So I'm stabilizing the formation of that p orbital. So I'm stabilizing, so this is where so you're forming, here's carbon, you're forming a bond to iodine, and you're breaking this bond to chlorine. So that's the rationale there. Okay? Are there any questions about that? Okay. All right. All right. So the other part of this chapter is dienes. Before we get into that, though, let's talk about a little more reactions that are at our disposal for allylic reactions. So more reactions at, oh, sorry, we should probably say of allylic okay, so you can form, well, yeah, a little carbon is special. So it'd probably be pretty useful if we can make that a carbon fragment and make it nucleophilic. So what happens when we add Mg here? What kind of reagent do we make? You got it, Grignard, our good friend Grignard. All right, so if you need to make a carbon-carbon bond, use a Grignard reagent, okay? So those will still be powerful tools for synthesis-type problems, okay? So please review a synthesis as well. So the problems in the homework, I think they give good variety. So if you could do those, I think you you'll be okay. And if you need practice, let me know. I'm happy to give you some more practice problems, okay? All right, so you can make Grignard reagents. You can also deprotonate and make lithium reagents, so very similar to a Grignard. So you would use butyl lithium. So 1, 2, 3, 4. All right, so the most common lithium reagent to do this is butyl lithium. 4 carbons, lithium atom on there. And then this is a solvent. This is to stabilize the lithium here. So this is just a solvent. If you put THF, I don't think it would really matter. If you just put THF or TMEDA. And honestly, if you don't put a solvent, as long as you don't put water in there, I won't take any points off, okay? So put a solvent. If you forget the solvent, I probably won't mind. So what happens here is that this now becomes our partially positive portion here. And then this has removed the hydrogen and made it negatively charged. So now my carbon is negatively charged. So I make a Grignard reagent, okay? And then the other part that, the other thing that comes off is butane. So that's your byproduct. So unfortunately, with lithium reagents, not very green, you're going to lose some alkane to the atmosphere, okay? So let me just give you a rundown of what happens here. This is the same as writing, this is now 2 hydrogens and a negative charge. All right, like this. In solution, in organic solution though, it doesn't exist as this. It's like a polymer. It's actually bonded. Okay, but in terms of reactivity, your carbon has a negative charge. Your metal is now positively charged. So we now have made a reagent that's very similar to a Grignard. Okay, so that's another thing. We can make now our allylic group electrophilic. We can then use that to attack carbon nucleophiles. Sorry, carbon electrophiles here. So let's use our newly made lithium reagent. So allylic lithium. All right, similar to a Grignard, it's going to attack this position right here. Okay, or it's equivalent. So, but it'll attack the least substituted position. So it's like an SN2 reaction. Okay, so I generate the O minus, like that. And then what does the water do? Anyone? What do you think the water does here? Is my source of hydrogen. Yeah, so I just protonate the alcohol there. So you just protonate the alcohol. So I decided to show that just in case we need to refresh on what the water's actually doing. It's just a proton source to isolate your product. Okay? All right. And then let's take our Grignard we just used. We can use the Grignard now. So these are not reactions specific to this chapter, but they apply from previous chapters where we use this in synthesis. Okay? So instead of an epoxide, maybe I can attack a carbonyl, ketone or aldehyde, THF. Okay, then 2 H3O plus. All right, what happens here? The ketone is not chiral, so you're going to get a racemic mixture here. So you get an O, then the H attaches in the second step. And then you're going to keep this methyl group right there. So since we have a pointer ketone, we can attack from both faces. So it's racemic. All right. And the other product above didn't have a stereocenter, so we didn't have to worry about racemic here, or not being racemic. All right. Okay, so that's just some applications. You can now use these allylic compounds to do carbon-carbon bond formation. So if you need a carbon-carbon bond formation, consider using a Grignard reagent or organolithium. Okay. Are there any questions? All right. So we expanded alkene reactions to allylic systems. Okay. So now we can actually talk about the another chemistry here. All right. So let's talk about dienes. All right. So now that's our next step, going to talking about dienes. Okay, so I know we've renamed dienes before, but let's just revisit that. Okay, so let's start with nomenclature. Naming dienes. I think we had to do that in last chapter in alkynes. Okay. All right, so let's say we have this molecule. And we need to name this one. Okay. All right. So, what's the parent chain? How many carbons? 7. All right. We have 2 alkenes, so is this going to be a normal alkene, or do we have a special name there? Yeah, we have 2 alkenes, right? So how do we name an alkene? We take the parent name, leave the alkane name, alka or hepta. So let's put hepta here. And then what goes at the end? It's not an alkene, right? What do we have? Diene. Yeah, you're right. Diene. So let's put diene right here. Diene. All right. So let's number these carbon atoms. So the bromines or the alkenes, what numbers should we give them? 1, 2, 4. I think if we number it this way, we won't have to worry about the substituents having the lower number, right? Or the higher number. So this is the way we should name it. So the alkenes start at what positions? 2? Yeah, that's right. 2 and 4. Good. All right. Now we can put everything together. Okay. Where are the bromines at? Yep, 2,4 dibromo. Okay. Then where's the ethyl? What's the other substituent? Yeah, you got 3. Oh, sorry. Maybe I should remove this a little bit. Three ethyl. Okay, all right, now I have to move it back. All right. So the last thing we have to recall is stereochemistry. What stereochemistry am I referring to? No, I don't see any like RS, but what do we have to worry about? The stereochemistry of? The E and Z. Yeah, E and Z, good. So the alkenes. Okay, so let's put in parentheses. So the first alkene is at carbon 2. We need to classify that as E or Z, okay? So let's look at these 2 positions here. All right, is bromine higher priority or methyl? Bromine. So bromine here would win. So this is our 1. This is our 2. All right, how about ethyl? Or the longer parent chain here with the bromine. Yeah, you want to use this group here. So this will be 2 and 1. So both of the higher priority substituents are on the same side of the double bond. So that gives us 2Z. Good. All right, now let's look at 4. We probably have to... Okay, let me erase a few things here. All right, we'll just erase these numbers. Trying to be gentle here. How do I go smaller? Okay, there we go. All right, let's look at the other double bond. All right. So now at this alkene, right here, we have an H. So we have H and this ethyl group. Ethyl will probably be 1, right? 1, 2. Now go back to the other side of the alkene. We have this bromine again and this carbon group. So remember here we have to look at the point of first difference. So which one has higher priority? Bromine or the carbon? Yeah, the bromine. So we're going to still put this as 1 and 2. All right, so they're both on the same. So the ethyl group on the left side and the bromine on the right side are still on the same side. So it's also 4Z. 4 is 2Z, 4Z, 2,4-dibromo, 3-ethyl, 2,4-heptadiene. Okay. All right. All right, any questions on that one? So you have to probably specify the stereochemistry if it's a linear alkene. If it's in a ring, don't worry about it. Okay. So let's do one more example, and then we'll take a little break here. Okay. So let's draw this cyclohexane. So we'll see some of these ring structures here. Okay, so let's name this one. All right. So the most important part here is numbering the carbons first. So let's see how we should number this system. Okay. All right. All right. Well, which position should get the 1? We're going to start at an alkane carbon or an alkene carbon. Yeah, alkene. So, I think the best one to do is where you have one of the substituents get the second number. So I think the best way to do it is do it this way. 1, 2. So when you're numbering alkenes, you have to go in the direction that includes both the alkene carbons. Like so. 3, 4, 5, 6. So I think this is the numbering scheme we should use. If we go the other way, the methyl will have a 3 position, and that's going to be less than 2, more than 2. So let's go with this numbering scheme. All right, 6 ethyl. All right, 2 methyl. Okay, and then this one a little different. We're going to use cyclo what? All right, if this one was hepta, what would this one be? Yeah, hexa. All right, so you can either put the numbers before the word diene. If you don't want to do that, you can actually put them before cyclo. So 1,3-diene, or whatever makes more sense. Either one, I will not take points off if you put one or the other. All right, so the reason why we had to put a dash here is because if we put the numbers in front, we had to do this. 1,3 cyclohexadiene. All right, so the numbers 1 and 3 indicate where the double bonds start. One starts at 1, the other one starts at 3. Okay, so that's cyclohexadiene. All right, so let's take a little break here, and then we'll come back and talk about conjugated dienes. Okay? All right. All right, and then once on that, when you're taking your break, I'm going to pass back the quiz from last week. Okay? Do, 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 do. Arjun, Evelyn. No, not today. Okay. Emily. Jessica. Yeah. All right. Catherine. Or Brianna. Here.
See, no, I have one, and I'm gonna have to go.
Evelyn. Betty. All right, everyone sign in. Yo.
I did this graph. That's an acid. Because you did say it was going to be like that, right?
Oh, it should be probably this one.
Because this is one graph.
Oh, no. So, no. So you should graph it at the same. So there's showing to be one set of data points. So I think it's this one. Yeah, it looks like this one.
So just get rid of this one?
Yeah,
Can
I think that's
just leave it? 'Cause
fine.
if you already
Okay.
submitted, that's why.
Okay. I think it's fine because the lowest here is at the 50 mark, so that's good. Don't know what's going over here, so there's a little weird dip here. Because what's your data points here? 80. Yeah, so the lowest here was at the 50, I think, right? 115. Yeah, so the problem is this was also 115. That was weird. So that's one of the weird points. And then this one, 80-20, that's lower than that one. So that one's weird too. But it's okay. We'll just take it. So it's good. Yeah.
And then I had a question on the actor.
Yes.
I have one attempt, so
Okay.
this one.
What you got? Yeah, what's up?
I have to leave at 4:30 because my dog has a vet appointment myself.
Oh, yeah, sure. Go ahead. Let's be recorded so you can catch up what you missed. Okay?
This one.
Oh, yeah. All right, we're actually gonna do something at the end. So just come make it up. It's like a activity. Just make it up with me in office hours if you can. Okay. I'll just tell you to do that. TikTok on an iPad.
Oh, it's because my phone's connected, so all my apps are literally
Oh,
on
okay.
my
Yeah,
iPad.
that's true. All right. So what? So remember H2, right?
Right.
You think okay, it's going to add hydrogen
Add
across the
hydrogen,
bond,
so-
but it's going to stop at what stage?
have to sketch
Is it going to go all the way to the alkane? No, it's going to stop at the alkene, right? Do you remember which alkene it prefers to form? Trans or cis?
Cis alkene.
Cis alkene. So you want to draw a cis alkene there.
Okay.
Yeah.
But it's like this one, right?
Yeah, you got it. Yeah, so you just had to put those R groups on the same side of the double bond. Yeah. You got it.
So 1, 2, 3, 4, 5, 6.
Yeah, there's around 6 carbons here.
And then alkenes at 3.
Yeah.
1, 2, 3. Like that?
No. So there should be a methyl group there. So put a methyl group there.
Right here?
Yeah.
Oh yeah.
All right, erase that. There's no methyl group there. So let's erase that. Remove. Okay. So this is where double bond should be, right? So let's put a double bond there. All right, but see here now, this methyl dot doesn't belong there, so just erase that.
Erase this one.
Yeah. Let's go back. Undo, redo. All right, let's what's wrong here. We have drawn, so 1, 2, 3, right? 1, 2, 3.
Mm-hmm.
Oh, but what kind of alkene is that? Is that the cis?
No.
That's the trans, right?
Mm-hmm.
So you need to put this 2 carbon groups down here. So I would first draw down 2 of them down there. So boom, boom, and erase those 2. Yeah, there you go.
Remove. I can't remove.
Why not?
Or I'll just draw it like that kind of.
Why can't you remove it?
It doesn't give me the option to.
Oh, now
There
you
you
can.
go.
There you go.
One,
So
two,
C, 4, 5, 6. So
Oh.
it's cis alkene. So you gotta be careful. You draw one way, it might be trans. Trans is the most stable. That's why it's zigzag like that.
Okay.
Okay? That's a cis alkene.
Thanks.
There you go. It's cute. All right. I think most of the arrows back. So let's just continue off. Continue where we left off. Conjugated Dienes. Okay, so I mean, conjugated has a lot of terms, meanings, like, verb conjugation. I didn't like that when growing up. But what conjugated dienes you have two alkenes, but they're not directly next to each other. They're kind of alternating. So double bond, single, double bond. Okay. Sorry, why did I write conjugation? Conjugated. Sorry. So conjugated means two, in this case, two alkenes or functional groups separated. One sigma bond. Okay. So in this case, our functional groups are double bonds. It can also be triple bonds, but usually double bonds in our case for our conjugated dienes here. Okay, so this is what a conjugated diene looks like. All right, so the double bond is separated by one sigma bond, so that's conjugated diene. Then non-conjugated, the double bonds are separated by at least two or more sigma bonds. Okay, so they're kind of like isolated. They're no longer conjugated. So that has some ramifications for the reactivity of these double bonds. So non-conjugated will act like a normal double bond, the alkenes. And conjugated, they'll have special reactivity, okay? So let's talk about first the relative stability of these double bonds, okay? And the way we quantify stability here for alkenes is by hydrogenation, so relative stability of dienes. All right, so let's start from the center. Cyclohexane. Let's quantify both these molecules, these cyclohexane rings, or, cyclohexene or cyclohexadiene rings. All right, so if we add two equivalents of hydrogen, palladium or platinum, and carbon, we're going to get two different values for the amount of energy or heat released. All right, so if we look at the non-conjugated diene, what happens here is the heat of hydrogenation is negative 56 kcals per mole. Okay? And then on this the left-hand side, this reaction gives off less heat. All right, so let's put per mole. Sorry, we should probably put per mole here. So, what this tells us is that when the alkenes are separated by a single bond, there is some stability associated with that. So, non-conjugated dienes, they're more unstable, so they release a lot more energy. Okay, and conjugated, they're they're more stable, so they give off less energy. Okay, so we'll see how conjugated dienes, like what kind of reactions they undergo. Okay, so when you have a conjugated diene, if it's not a ring, you can have two different conformations. So we can have the diene like this. Okay, so when it's in this conformation, your hydrogens on the end here, they're not going to be too happy because they're going to clash right here. Okay, so this is S-cis. So this is the S-cis conformation. Because if you look at a diene, it kind of looks like an S. So let me draw the other conformation here. So if we rotate around the single bond, you'll get to the lower energy conformer. So you'll release some energy. And to get back to the cis conformer, you have to put in some energy. So it's plus 3 kcals. So if I rotate around that single bond, I can then get this conformation. So this is called S-trans. Now the hydrogens are now out of the way of the other hydrogens. Okay, so it looks like an S, so that's why we call it. Okay, that's a bad S. You know, it kind of looks like an S in some ways. So that's why we call it S-cis, S-trans. You don't really need to write that down. All right, so these two, the relationship here. Remember when bonds rotate, right? What do we call that? These two are what? Not isomers, but conformers. Do you remember that? Do you remember chair structures? Those are conformers. Do we want to draw chairs? No? Okay, I won't. You had enough in an A. So conformers of conjugated dienes, okay? All right. So in your homework, you'll see alkene reactions again, and they may seem familiar, but we're applying them now to dienes, okay? So alternating double bonds right here, okay? So let's go over some reactions that we saw before. The first one on our agenda, electrophilic attack or addition. One, 2, and 1, 4. I'll explain what these numbers mean in a bit, but 1, 2, and 1, 4 addition, okay? So, last time, previously we saw alkenes react with HBr, alkynes do the same thing. All right, so I'm going to mention a few things here. All right, so if you have two temperatures and one is very lower than the other, that favors kinetic control, okay? So 0 degrees, very cold. All right, so the product we get is a mixture, but they are so different that we can isolate them, okay? So you're going to get 80% of the kinetic product. The kinetic product is the terminal alkene, okay? So kinetic product. So this is called 1,2 addition. So when you have the double bond at the end, that's called 1,2 addition. Because what two carbons did I add HBr? Which carbon numbers did I add HBr? Was it carbon 3 or carbon 4? It was these two carbons, right? So this is, let's just write that. Let's just note that. Carbon 1, carbon 2. If I add them across carbon 1 and 2, that's called that's called 1,2 addition, okay? And we get this in 80%, so pretty good yield, okay? So at low temperatures, you have something called kinetic control. You're under kinetic control. All right? So kinetic control is usually favored by low temperatures, or short reaction time. So what does short reaction time mean? Okay, so like if you have a reaction that takes 2 weeks, is that considered short? 2 weeks to run a reaction? Really? No. Okay, short reaction time is like 20 minutes, 5 minutes. Okay, it's a very short reaction time. On the homework, you won't actually see short reaction times. What you will see is temperature, low temperature. Okay, low temperature is what you'll see. All right, so now the other product, what else forms, is the thermodynamic product, but in much lower yield. Yeah, 20%. Okay, so so there's a big discrepancy there. We can push the reaction to one product, so that's useful, especially if the products form a mixture. So this is called thermodynamic product. So this is called 1,4 addition. And if we write where the hydrogen is, the hydrogen added right here. Okay, so you have another hydrogen right there. The hydrogen is at the 1 position. The bromine is at what position? What number? Yeah, at 4. So we just count over there, that'll be 4, right? Yeah. So that's why it's called 1,4 addition. You added the bromine several carbons away from where you added the hydrogen, so 1,4. Okay. Now we can actually flip the switch here. If we change the temperature, go to longer reaction times, let the reaction be able to equilibrate back and forth, you can isolate the thermodynamic product in good yield. Okay? But are any questions? Does anyone need me to go over that again? Are any questions? What question is, bro? All right. So let's talk about how does this work? So how does this add to one double bond, and how do we get to the other product? Okay, so here's the mechanism. So let's talk about the mechanism. So we have HBr. This alkene is going to grab a hydrogen atom here and generate a carbocation. All right. Where do you think the hydrogen will go? Where do you think the carbocation will form? What's the more stable position? Does anyone have an idea? All right, so am I going to put the hydrogen on the last carbon or the third carbon? The last carbon. So we should put the carbocation right here. And the reason we put the carbocation right here is because what's special about this carbocation? What can it do? Or why is it more stable? Yeah, you got it. Resonance. That's kind of the buzzword this semester. Resonance. It's going to explain a lot, okay? So it explains why this carbocation forms at this position. It's because you can then put the carbocation on the other carbon on the end, on the other side, and now you have these two structures as intermediates. Okay? So similarly to how we, generated an allylic carbocation, you're doing the same thing here, except you have two double bonds separated there as your starting material. All right, so let's talk about the formation of the kinetic product. All right. So you're going to use the more stable carbocation. It's secondary, more stable. So bromine is actually going to attack right here. And then this reaction is reversible. So you can actually go back and forth. So let's put equilibrium arrows and we get the kinetic product. The secondary allylic bromide right there. So that's the kinetic product. All right. Now let's talk about the thermodynamic product. All right. How would the thermodynamic product form? Which carbocation should we use? The more stable one or the less stable one? Yeah, the less stable. We're going for the more stable product overall. So we're going to use the internal alkene here to form the thermodynamic product. So Br is going to react with this carbocation, and we get Br. The primary allylic bromide there. Okay. All right. So most of the time alkenes, I don't know about most of the time, but sometimes it won't be symmetrical. So you can also have attack on unsymmetrical alkenes, dienes, sorry. But are there any questions first before we move on there? Is there any questions about this one? Okay. So two different products can come out of this reaction. And that's based on the carbocations there. So, well, what if you're starting diene? What if it's not symmetrical? Sometimes that can happen. So let's say electrophilic attack on unsymmetrical. Conjugated. All right. Okay. So HBr here. Now we're going to specify higher temperatures. So this will actually affect the the product outcome, okay? So what happens here is you will form this product, the tertiary bromide here. However, this only forms in 6%, so this is not the major product. And this pretty much forms through this carbocation via this carbocation right here. All right, so that carbocation, that's pretty stable. It can do resonance, but also it can do, it's tertiary, so that's pretty stable. But the alkene is still considered less stable, okay? But what if we move this double bond, and now we generate the more stable alkene here, the tri-substituted alkene, okay? So if we do that, we can get the other product. So this will actually go through, okay, and give you this other product. So let's draw the, let's move this alkene over here. Then we get Br. So this occurs through this, through this carbocation, okay? Through this less stable carbocation, okay? So under these conditions, this is present in 94%, so this is the primary product. So at high temperatures, what kind of alkene are we going to favor? The more stable alkene or the less stable? At higher temperatures. So under this control, so this is under thermodynamic control. Okay, so what does this mean? The conditions here, high temp, okay, or comma, long reaction times. Okay. So if you let something go in equilibrium, so say this one forms, right? This product forms. So this product can form here, okay? This product can form, but it can equilibrate back to this carbocation like this. And this carbocation can go back and forth. Well, it's not back and forth, but this carbocation can eventually, this carbocation can persist until eventually this product is favored. Maybe I should do it like this. Until it goes to this Br, okay? This bromo compound. So if it has time to equilibrate, so it'll equilibrate. It will equilibrate. It will give you the dermo product. The dermo product here. All right. If there's not enough temperature or enough time for this reaction to equilibrate, it's going to go to the kinetic product. So that's the difference. Temperature, reaction time. Those are two variables we play in the lab to kind of figure out, is there a way we can get to this product instead? So sometimes it's like a game. Okay? All right. Okay, tertiary bromination. All right. Yeah, well. All right. So what are the common reactions for these dienes? There's really two types. HX or X2. So let's go over bromination this time. And I want to actually talk about this because I want to bring back some discussion here. All right, so conjugated dienes, okay, can also undergo bromination. All right. All right. Do you guys remember the mechanism when an alkane attacks BR2? What was the intermediate that formed? It was a special intermediate. Do you guys remember that one? So previously, we thought, okay, here's my alkene. All right, BR2. The alkene would attack, and the lone pairs on the bromine would attack at this other position. We get a bromonium intermediate. Okay. And then eventually bromine here would come around and attack in an anti-fashion here. Okay, and you would get the trans-bromine addition. Anti-addition. Okay. And it was usually at, well, actually, was it at the least substituted position or was it at the more substituted position that bromine attacked? I think it was the opposite, right? Let's actually modify that a bit. My bad, guys. Okay. Bromine actually attacked at the more substituted position. That's because there's more partial character here, partial positive character here, and like that. So we actually got a racemic mixture. Oh wait, actually I don't think I had to put it up like that, but BR, and then you had a BR over here too. So this is something I'm just recalling back from our knowledge here. So we get racemic mixture because the bromine could form this intermediate above and below the plane, okay? All right, but what actually happens, so this is previously with just one alkene, but what actually happens is we get two different intermediates. So bromine would add to one alkene, okay, but it does not really form this intermediate because if we do form this intermediate, it's not resonance stabilized, okay? So what actually happens is if we, let me just slightly represent this as BR2, BR, BR. So this is going to attack bromine, kick off one of the bromines, and you get the carbocation. Okay, so we get this intermediate, and this can have a resin structure now as bromine. And then, so previously we would have this intermediate, but when we have a diene, that doesn't happen, okay? So this does not form, so this intermediate here does not form, okay? And so then once we have bromide ion right here, Br minus, we can get two different products now, okay? So this temperature is actually not very specific. The reaction time is also not listed. So it turns out if we do this reaction, we actually only get a approximately 50-50 mixture of both isomers. The kinetic product, 1,2, 54%. And then plus B, only 46% of this one right here. Okay, so it's not as clear cut here. The conditions still favor, well, it's not kinetic or under kinetic or thermodynamic control. It's actually under the influence, it seems like, of both. There's really no preference here. And that's maybe because the temperature is not too cold or not too hot. So that might explain why it's 50-50. All right, so the intermediate is a little different. So when you have a diene, you're going to form a carbocation. You're not going to form a cyclic bromine intermediate there. Okay, so that concludes our discussion here of adding electrophiles to dienes. Are any questions? No? All right, so now we're getting to the cool stuff. I know that was pretty cool, but this is even cooler. So we're going to talk about one of the most famous reactions in all of organic chemistry. It's called Diels-Alder. So what makes Diels-Alder so cool? It's a cycloaddition. So you're bringing two molecules to come together. They form a ring. And the beauty of this is that there's really no other reagent you need. You need a solvent, but that's pretty much it. So the cycloaddition of ethene, so the classic Diels-Alder is ethene and the simplest diene, conjugated diene, 1,3-butadiene. All right. Okay, so this is called 1,3-butadiene. All right, so here it has 4 pi electrons. So there's 4 electrons in the pi bonds, okay? So this is a diene. All right, ethene here. How many pi electrons are in ethene? Yeah, 2. Good. Just 1 pi bond, so 2 pi electrons. Very good. All right, so one component is the diene. All right, you probably heard jokes about, this molecule. It sounds like I'm dying, okay? And then the other group is called the dienophile. So it wants to join up with a diene to form a ring, okay? So alkene, dienophile, okay? Diene is the one with 2 double bonds. All right, so if we heat the crap out of this to 200 degrees Celsius, you will furnish a reaction where the 4 pi electrons will combine with the 2 pi electrons in the alkene, and this is called a cycloaddition. So this is what we call a cycloaddition, and the cool part here, you form a cyclohexane from 2 compounds like that. Okay, so this is called cyclohexene. And look what the beauty of this process is. Is there any byproducts? Is any byproducts generated? No, you only have your target molecule, so this is very green. The atom economy is spectacular, okay? You have no waste stream, so this is like one of the best green reactions we can ask for. So this is a cycloadduct. All right, so this is about 20% yield, very poor, okay? So not good. But let's just summarize the key bondings that are forming, okay? So here you have 4 sigma bonds and 3 pi bonds. And what I'm talking about here is the carbon bonds, not the hydrogen, so carbon bonds. Over here, you are forming 6, you're getting now 6 sigma carbon bonds and 1 pi bond. So for carbon. Okay? So why does this happen in the first place? Well, it has to do with the pi orbitals, but if we exchange pi bonds into stronger sigma bonds. Well, I would say it's stronger, but, well, yeah, so the bonding itself is stronger. You have direct overlap of atomic orbitals, so that's why it likes to substitute and form more sigma bonds. So that's the driving force, okay? All right. So let me go over a few more things here, and then we'll do a little something at the end, and then we'll call it a day. So concerted, intermolecular, cyclo addition. All right. Okay, so why does this happen? If you draw the skeleton here, it looks like the p orbitals want to combine here and form what we call a cyclic transition state. Okay, so when you have p electrons being distributed all around in a circle, that's called a cyclic transition state. And that's what's known as a pericyclic reaction. But don't worry too much about that name, okay? So what's happening here? What's the mechanism? Well, there's no polar intermediates. There are no positive and negative charges. So this must actually happen all at once. So what happens here is you form a single bond there, change this into a double bond, and change this into a single bond. And then if we kind of trace what's happening here, we get a ring structure. And that's the beauty of that reaction. You get a ring structure from these two carbon fragments, okay? And this is just the entry point. You can actually do this when you have a very complex molecule. So a lot of reactions kind of follow this trend here. All right, but what I was talking about here, the yield is not that great. So you can actually tweak the reactants here to make it better, okay? So let's talk about that. The yield can be improved with different dienes and dienophile. All right, so you want an electron-rich diene and electron-poor dienophiles. All right, so I'm going to copy this down. But I want you to tell me on a piece of paper which one of these molecules is considered electron rich and which one of these is considered electron poor. Okay, so let's recall, how do we tell if something's electron rich and electron poor? Okay, so write that on a piece of paper or note card, and please, when you write your answer, please turn that into me. And then we will talk about this next time, okay? All right, so write down these two molecules, and under one, put electron rich, and under one of them, put electron poor, okay? So tell me which one's electron rich, which one's electron poor, and then we'll talk about that starting next time on Thursday in class, okay? All right, that'll be it. Use what